So a little bit more complicated slider, inverted slider crank is the following. It is, you have a crank, connected to it is a slider like this one. Okay. Now, connected to this one, the slider slides on a rigid link like this. The slider slides inside this link, but this link has a rigid connection like this one. This is also an inverted slider crank. The thing is, this thing is like welded here so that this angle is fixed. Okay, so it is A0, B0, let's say. This point, let's call it C for some reason. And this is A. Again, the numbering of links is 2. This is 3. The slider is 3. And the thing the slider slides on is 4. Angles, theta 1, 2 is one angle.
What's his number? 3?
Number 3 is the slider. This angle is, let's say, theta on 4. And let's say that we have this thing, there is an imaginary line, and let's call this angle alpha. Or you can call it alpha 4, but it doesn't matter. But there is one more thing that is necessary here. We need to give link lengths. The link lengths A0A, which is A0A is the link 2 length, is A2. This is straightforward. We have to say B0C. Let's call this B0C. We have to say these are the lengths of these, by the way. B0C is, let's call it A4, okay, this length. Now, this length CA is a variable, okay? By the way, A0, B0 is a fixed length also. A0, B0 is this thing. Let's call it A1. These are all fixed. This distance, AC, is a variable, as we see, and we call it S43, or we might call it S34. It is kind of the same thing. CA distance is S43 is a variable. Theta 1, 2 angle is a variable. Theta 1, 4 angle is a variable. Another constant, another thing is alpha, by the way. This alpha angle is fixed as well. So these are variable, and usually this is the input. Okay. Alpha is a fixed quantity as well. So it's here. So we will try to write the loop equation. Let's try to draw it here. We will say that A0A, this vector, well, let me try to draw it not here, but somewhere else. Let's draw it here. This A0A is equal to A0, B0 vector. Then you have B0C vector, okay? And then you have CA vector. So A0, B0, C, and A. In short, we can write A0A is equal to A0, B0 plus B0C plus CA. Okay. Now, in the complex number notation, it is A2 e to the I theta 1, 2 equals. This is A1 plus B0C is, what was it? A4 e to the I theta 1, 4 plus CA. CA has a link length of S43 and its angle. What is its angle? The angle here is, well, up to here it's theta 1, 4. And here it is alpha, so it is e to the I theta 1, 4 plus alpha. Okay. S43 is a variable here. Theta 1, 4 is a variable. So we have to note that CA changes in magnitude and direction. But the CA vector's magnitude changes because S43 changes, and its direction changes because theta 1, 4 changes, as you see. So inverted, this is a more complicated version of slider crank. The easier slider crank was when you had this part A link connected to B0 by another link. No, by a link like here, okay? That is, it was something like this. This is what I had drawn the last time, as you might remember. Okay, this is the inversion of a slider crank mechanism. That is, in the slider crank, instead of fixing one link, we fixed some other link other than, well, we fixed another link and we get the following slider crank mechanism. This is a, commonly used mechanism. This is more complicated. So I guess we have, do you have any questions up to here about this? Okay, so we are talking about loop equations, but when we say loops, we might have, actually, it is possible to have multiple loops. Until now, we have looked at loops, well, mechanisms with single loops like this one, for example. There was only one loop here, as you see, in a 4-bar or in a slider crank like this one. There was a single loop equation. Okay, you just write, well, there is only a one vector equation you could write here. That is, this one plus this one is equal to this one plus that one. Or you can say this vector plus this vector is equal to this vector. So there is only one loop, as you see here. But it is possible to have multiple loops. For example, these are single loop. For example, I can give you a very simple example. Well, we start with a 4-bar again. And to it, we connected another, well, kind of another 4-bar like mechanism. Okay. As you see, we now have 2 loops. One loop here and another loop here. So here we have or you might have even more, 3 loops or something. For example, let's say, sorry. This is 1, 2, 3, 4, 5, 6, let's say. I can give you the following example, for example. This is from your textbook. These are rigid links, all are fixed. Connected to this is okay, something like this, let's say. Let's number them. Let's say that, let's number them in a different color. Let's say this is 1, this is 2, 3, 4. Let's say you have 9 links, let's say. Well, yes, the ground, we didn't ground anything yet. For example, we can ground this link and it will be the ground. Okay. This is a mechanism without, without any ground. So the number of links is 9 here. Number of joins, we can count them. Let's say that they are all revolute. 1, 2, 3. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? J is 11 here, number of joins. Here you have a multiple join, so you have 2 revolute joins here. Otherwise, they are all simple. Well, there is a famous formula used in graph theory. Again, it's due to Euler, polyhedron formula, which relates the number of loops to joins. So the number of loops is equal to, according to this, the number of joins minus the number of links plus 1. Okay. For example, here we will have number of joins 11 minus 9 plus 1, which is 3. As a matter of fact, what are they? 1, 2, and 3, you can say. Well, there might be a number of independent loops are these ones, okay? And we can find, for example, for such a mechanism, we can find the degree of freedom. As you might remember, it was lambda, what was it? L minus J minus 1 plus sigma Fi. Let's say it is 2-dimensional. L is number of links 9 minus 11 minus 1 plus. And these are all simple links, so it is 11. So the degree of freedom is 2 here, but the number of loops is 3. You might have, for example,
Hocam, is it possible if you can write the joints, like
you used to write R and R, like 2R. Could you,
Yeah,
if it's
okay.
not too much?
It is not too, I didn't want to spend time on it, but. Here you have two revolute joints, so it's 2R, R, R. That's all I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Hmm? Okay, the loops are that. Okay, this might be one loop. This might be one. This might be another one. For example, or these are three independent loops. Or you can, for example, select this whole thing as one loop. Okay. Let me use another color here. Let's use this one. This is one more loop, but these two loops, the loops, the green one will be actually the equation for the green one will be dependent on the equation, on the red equation. So there are only three equations. Okay, three vectors equations can be written. And also there is another thing which I will give you without proof. The number of variables, the V is equal to 2 times the loops plus the degree of freedom. So it is 2 times 3 plus 2 is 8. There will be 8 variables here in this equation. And we know that each loop equation can be solved for 2 variables, okay? Let me write it here. Why is that? Because in the 2 dimensions, each loop equation represents, well, can be, has 2 components. Therefore, it can be solved for 2 variables. And we have 2 degrees of freedom, which will be the inputs. So the number of variables will be 8. 2 of them will be independent. These will be the independent variables. And 6 of them will be dependent, which can be solved from our equations. Okay, let me give you this example of a quick return mechanism now for multiple loops. Do you have any questions about this first? Okay. Another thing is, again, I can, for example, in this 2 4-bar example, this might be one possible loop as well. Okay, the green one. But the green one will be dependent on the red ones and vice versa. So there are only 2 possible loops. And I will illustrate this with an example now. So our example will be the quick return, the so-called quick return mechanism, which is something like this. Let me show it to you. Let me draw it here. This is fixed is another fixed point. So, that's well, this thing goes inside the link, inside the slider. Okay, you can understand that. I should be erasing this part, but I cannot. So just understand that. This is B0, this is A0, and this is continuation of A0. Let's call it point D. This is A, this is B, and this is C. Okay, this is a quick return mechanism. The crank that keeps on rotating is A0A, as you see. Okay, and it makes this slider C go back and forth. And usually the way it returns is much faster than the way it goes in one direction. So let's try to enumerate. This is 2. This slider is 3. This one is 4, B0B. This is 5. And C is link 6. Okay. Now for the variables, this angle is theta 1, 2. This angle is theta 1, 4. This angle is theta 1, 5. These are variables. Okay. Now 3 is this distance B0A is a variable. So this distance is S3 with respect to 4. You can say S3, 4 or S4, 3. It doesn't matter really. And this distance is a variable too, this distance, which we will call S16. Now for this mechanism, the degree of freedom of space is 6. The number of links is 6. Degree of freedom of the space is 3, I'm sorry. The number of joints, J, is equal to what? 7. It is 1, 2, 3, 4, 5 revolute joints. and two prismatic joints, as you see, 1 and 2 here. So it is 7. So we can find its degree of freedom. F is equal to 3 times 6 minus 7 minus 1 plus 7, which comes out to be 1. Okay, the degree of freedom of the mechanism. Now the number of loops is J minus L plus 1, which is J is 7 minus 6 plus 1 is 2. We have 2 loops. And now the number of variables is 2 times loops plus the degree of freedom, which is 1. So it is 5. So there will be 5 variables, which are, the variables will be the following: theta 1, 2, theta 1, 4, theta 1, 5. These are the angles, S3, 4, and S1, 6. So these are the variables. What about the fixed quantities? A2 is the link length of link 2. For link 4, we have A4. Okay. For link 5, we have A5. What else do we have? We have another thing. A0, B0 is A1. Okay, so A1 is A0, B0, this distance. But we need one more distance actually, which is this A0D, let's say, or we can use B, well, let's use D0 here instead of D, because let's say that the fixed points are D. So we can say B0, D0 distance is, what do we call it? B1. Okay. And also we have A2, A4, A5. So these are fixed quantities. Now for the mechanism, there are 2 loop equations. Loop 1, for example, can be the following. It is this quick return mechanism over here. A0A is equal to A0B0 plus B0A. That's one loop. So you have one loop here. This one, okay? So I can write it in complex number notation as follows. A0A. A2 e to the I theta 1, 2 equals. Now, we go A0, B0, okay? Which means we go downwards in the vertical direction, okay? And that will be minus I times A1, okay? Because we are in the complex plane, like this is X, this is IY. We are writing our equation in the complex plane. Plus, we go down now, and we go up B0A. B0A is, magnitude is S3, 4, and its angle is theta 1, 4. E to the I, theta 1. So that's one loop equation. The second loop equation is, for example, it can be this one, B0, it can be it can be, for example, A0A plus AB plus BC is equal to A0 D0 and D0C. Or I can write the large loop equation, for example, B0B. This is what I have written, and this example is from your book, so let me replicate it. BC is equal to which is this B0B. What is this? B0B, this one, B0 to B, plus BC is equal to B0 D0 with this whole thing from here to here, and D0C, which I can write as following. B0 D is A4, no, not A, yeah, A4, e to the I, theta 1, 4, plus BC, A5, e to the I, theta 1, 5, will be equal to B0 D0. So it is in the vertical direction, so it is IB1 plus this whole distance, it is S1, 6. So this is another equation. Note that I can write another equation, which is the following. A0.
Hujam,
yes.
Hujam, you're taking in loop 1, you also took it as IA1, and then you took IB1. So B1 is basically the distance from B0 to D0, but you didn't mention it, right?
Yes, this distance is B0.
B1.
B1.
Okay. And I, because it's vertically, so consider that.
Huh?
So when so you consider the whole distance like this,
yes,
and
yes.
we're going upward, so it's positive.
Yes, that's right. Another possible loop equation is A0A plus AB, okay, plus BC will be equal to A0 D0, sorry, plus D0C. But this equation will be dependent on the first and second loop equations. So let's say this is 1, this is 2, let's say this is 3. This is dependent on 1 and 2. Actually, by adding and subtracting these 1 and 2, you should be able to obtain the third equation. Okay, it's not too difficult. So there are only 2 loop equations that are dependent, that are independent. I'm sorry. The second loop equation is something like the bigger one, this one. So any other loop equations you would be writing would depend on these 2 equations. So the number of independent loop equations here is 2. Okay. Any questions up to here? Well, before we formulating the loop equations, I think we have done enough for that. From this point on, I will try to get to solve these equations. How do we solve these equations in order to obtain our unknowns? Okay, that is the dependent variables. For example, for this case, let's say that this is our input. We have the variables are, let's say, are these. If theta 1, 2 is given, then you have to find 4 variables in this case. Or in the case of, let's say, inverted slider crank, you have to find 2 variables with 1 loop equation. Or with 2 loop equations, you have to find 4 variables. How do you solve these equations? These equations are given here. This is one equation. Okay, this is another equation. Actually, these equations contain 2 equations inside them. So in principle, they should be solvable. 4 equations with 4 unknowns. But the problem is that they are nonlinear and they require, well, some ingenious techniques to solve them. And their solution is not very easy. Usually it requires, well, making some tricks. And in general, in the most general case, actually these equations might be solvable only by using numerical techniques. That is, no closed form solutions might be possible. But for the solutions, we usually commonly use something which I want to remind you is the sine and cosine theorems, which you probably know from high school or something. Let me see if I can draw a nice triangle here. Probably I cannot. No, this is just a okay, I can do the following. Okay, let's suppose that this is a triangle. So its sides are A, B, and C, and its angles are A, capital B. Well, you know this, but this is just a reminder for you, since we will be using this. The cosine theorem says that the c squared, the square of this side, is a generalization of Pythagoras theorem. So it is this length is equal to, length square is equal to a square plus b square minus 2ab cosine c. Or you can find, for example, the angle from here as cosine, let's say, c will be equal to something like this. Okay, this is the cosine theorem, and the sine theorem says it's even simpler actually. It is sine A over the length A is equal to sine B over the sine B angle over length E is equal to. This will be these trigonometric relationships will be very useful in the analysis. And using these and the loop equations we have and the geometry, we will try to solve for the unknowns of for our loop equations. Okay, so let's try to do that in the next hour, and let's take a break here. How do I stop? Okay, now we are recording again. And we will be looking at how to solve the loop equations. So, well, one technique is graphical. Okay, this is not a what happened? Well, this is not something we use that much nowadays because it is kind of old and difficult to do. But let me give you the idea about this, how you do it. Let's say that you have a 4-bar mechanism like this one. Okay. So what happens as the 4-bar moves is this thing, let's say this is A0, this is B0. This thing traces a circle, right? So it makes its path is something like this. So in another instant, later on, this link comes to somewhere around here, let's suppose. Okay. Now, this link, which is connected to the ground, also traces a circle. So it will be doing this. We will find a position for this link. Let's say something like this. So that the distance between these two things, these two links, remain constant. For example, what's going on? So this is A0, A, B, and this is A0, let's say A prime, and this position will be B prime, okay? So from this position, oh, sorry, which was it? This position, your mechanism comes to the following position, and we can keep on rotating this. So A goes to A prime, B goes to B prime. So how we can do is, we can graphically use a compass and open our compass the length of AB, let's say, and draw a circle from this A prime to this circle B, and then that circle will intersect at B prime, so that you will find the position of the mechanism, and so on. So you just going like this all throughout that circle, you can find the position of your mechanism as this thing goes on, okay? Or you can do the same thing, for example, for a slider crank mechanism. Let's say this is your mechanism. This is your crank. So what happens is when you come here, for example, that's not a very good way of drawing it, but this everything so that I can draw it. Let's say that this is our slider crank. The crank, this one, which is A0A, let's say, rotates, it traces a circle, as we know. Okay. Perhaps a larger one. So when the crank comes to another position like this, A prime, our slider is going to go along a straight line, as we all know. So what we do is we just take again a kind of a compass and find, take the length of this AB and find how it is displaced. Let's say it comes to here, so this will be B prime, this will be the position, and this will be our new position for the slider crank mechanism. And we can keep on doing this for all 360 degrees, and then plot our this distance. Let's say if we call this distance S14, we can plot S14 versus theta, and it will be something like this, as a matter of fact. Let's say this is 360 degrees, this is 100 degrees, etc. Okay, you can find the position of the slider crank mechanism for all positions. Now, this is the graphical technique. It is possible to do it, but this is something that was used in the pre-computer times, like in 1960s or something. And after that, it is really becoming unnecessary to do this, but still, to do this gives you quite a bit of insight. So keep that in mind, that it is possible to do this thing graphically, but not many people do it nowadays. You can do it graphically using a computer program, perhaps. So other possibility is the stepwise solution, which I will go through for a few mechanisms. This is possible for simple mechanisms. Well, for, let's say, Let me give you the example of a slider crank here. Slider crank is especially kind of easy. Let's say this is the crank. This is the connecting rod. This is the slider. This is the eccentricity C, we call it. So the loop equation is A0A is equal to A0B plus BA. So this vector is equal to A0B plus BA. So we can write A2 to the I theta 1, 2 is equal to S14 plus IC. IC is the horizontal vertical component plus A3. So we separate the real and imaginary parts. Let's say that this is 2. So from 2, we can say, for example, sine theta 1, 3 is equal to A2 sine theta 1, 2 minus C So you can solve for theta 1, 3. And if you solve for theta 1, 3, you can solve for S14 from 1 simply. S14, since S14 is solved now, sorry, theta 1, 3 is solved, S14 can be solved from A2 cosine theta 1, 2 minus A3 cosine theta 1, 3, from which you can solve for S14. You can easily program this on a computer or a calculator or Excel or something, for which you can obtain the values of theta 1, 3 and S14 for all possible values of theta 1, 2, for example, given the parameters. This is, as I said, is especially easy for the slider crank mechanism. This is the slider crank. A little bit harder. Any questions about this, by the way? Is the 4-bar mechanism. 4-bar can also be solved by stepwise solution. Let me try to draw a nice 4-bar here. This is A1. Okay. Now, to solve for the 4-bar mechanism, given theta 1, 2, we want to solve for theta 1, 3 and theta 1, 4. Well, we do a trick, which is to construct a line like this, okay? And we call this distance S. Now we have divided the 4-bar into, as you see, 2 triangles. And the 2 triangles are easier to work with because well, we have sine and cosine theorems for those triangles, basically. Let's this angle we will call mu. This angle we will call it's not very well drawn here. At this angle I will call it phi. And its complement, which is this one, okay, this angle, I will call it phi prime, although it should be closer. Okay. So using these two triangles, A0, B0, and A, so for triangle A0, A, B0, we can write the following. S, for example, this distance from cosine theorem can be written as A1 squared plus A2 squared as 2A1, A2 cosine 1, 2 to the power 1 over 2, right? This is cosine theorem. What is unknown here? Nothing. So you can find the S value very easily. So now A1, A2, and S is known. So that phi prime, this angle that is over here, can be found from cosine theorem also. Phi prime can be found from, let's say, cosine inverse of okay. We are not done yet though, but phi prime can be found, from which angle phi can be found. Phi is this whole angle. It is simply pi minus phi prime. Okay. So phi is found. Then we go to the other triangle. For triangle A, B, B0. That is the upper triangle, A, B, B0. Okay. You can find certain angles. For example, the angle mu can be found. Now S is known, as we know. Mu can be found from, we will come to this plus minus business. It is again the cosine theorem. Mu is called the transmission angle, by the way. Let's just keep it in. And psi angle can also be found. But we didn't find theta 1, 3 yet, but we will. So inverse. Therefore, squared it should be, right? Now we can find this. Then theta 1, 4 is simply phi angle minus the psi angle. Okay, you can see it from here, which can be found. And theta 1, 3 it's not very obvious, but I will show it to you. It is theta, once you solve for theta 1, 4, it's theta 1, 4 minus mu. Why is that? Because we have, let's say this is theta 1, 3. This is theta 1, 3. This is mu. And this is theta 1, 4. Okay. So that this angle, theta 1, 4 has to be the, what will that be? Theta 1, 4 should be equal to theta 1, 3 plus mu, right? Yes. So you find that theta 1, 3 can be solved from here. So the solution is stepwise. We first solve for S, then solve for phi prime, then solve for phi, solve for mu and psi, and using these, you solve for theta 1, 4 and theta 1, 3, which means that this thing can be programmed to a programmable computer, as you see, or you can write a kind of an algorithm in order to solve for the unknowns of the 4-bar. Can you follow this? It's not very easy, but it's a little bit, you know, it's complicated in terms of equations, but understandable. It's just by step you solve for it. One thing that is not obvious is this part. What is this plus minus thing? Okay. This plus minus thing corresponds to the cross position of the 4-bar mechanism. Again, let me, I wish I could just copy it from the previous page. Is it possible? Sure. Okay, let me try to do it. Select and copy. No, I can just move it like this, but huh? Control V didn't work. Almost didn't work. Anyway, I have to do it again. Well, for this transmission angle, there are two, for a given transmission angle, that is, there are two possible solutions. One is this one, okay, the regular position. The second is, for this angle mu, there is one more possibility, and it is this one. Suppose that this angle is equal here, so this is so this mechanism for a given transmission angle mu, it has two possible positions. This one is called the cross position of the mechanism. Okay. Therefore, the solutions we obtained in the previous page has two possible solutions, plus and minus. For the same theta 1, 2, that is, for the same crank angle, theta 1, 2, we have two different solutions. Okay. Okay. Another possibility, by the way, let me just repeat here. We found phi prime and phi from this equation, as you see. We first found phi prime from this triangle, and then we found phi. There is another possibility here. Let me try to show that. Let me use some different color. Let's say that this is S, and this is phi. Let's look at this triangle now. A0, AB0. We can find phi directly without finding phi prime as follows. We can say that, for example, S as a vector is equal to B0A. And we can write it as, in complex numbers, Sx plus Isy. But S is directed towards the left, so the Sy quantity, Sx quantity is negative. So you can write Sx to be equal to A2 cosine, this is A2, theta 1, 2, minus A1, and this is a negative quantity because S is directing towards the negative anyway. And then Sy is equal to A2 sine theta 1, 2, okay? In which case, we can write phi angle to be tangent inverse of Sy over Sx, okay? This is, just not to confuse you, this is just a, let me remind you here. This is another way to solve for. Okay. Possibly this might be easier to program on a computer than the previous one. That's why this is sometimes used. Okay. Any questions up to here? Let's go through the inverted slider crank. Inverted slider crank, as I have drawn before, is the following mechanism. Okay, this is the mechanism we have in hand. Let's call this position B. This angle is a rigid angle. Okay, this doesn't change. What we do is we construct a line like here. And we call this P. The length of it is P. Okay. The angle between the ground and the P, this angle, is called phi. And this angle between B0B and P, this angle is called psi. Okay. So now we look at this triangle A0, AE0, and we can write the following. In this triangle, we have something like this. This is 1, 2. This is P, and this is A1, right? Just as we have done before, P cosine phi is equal to 2 cosine 1, 2 minus A1, which is this, you know, the cosine of this angle has to be negative, so that's why we have a negative quantity here. And then P sine phi will be equal to 2, from which phi angle can be found easily. Phi is simply the tangent inverse. You divide them to each other, 2 to 1, of and P distance can easily be found. It can also be found from cosine, law of cosine, actually. P squared can be found, but you can also use Pythagoras theorem, whichever you prefer. P will be and then For one thing, for this example, there is a reason why this is a little bit easier. This angle, let me, sorry, undo this. This angle is a, right angle, okay? It's a fixed angle and a right angle. That's why we can easily write this cosine inverse C over P. The C is, by the way, this B0B distance. This example, again, I have taken from your book. Yes, yes, the right angle is given. Yes. I'm sorry? A4? What is A? Did I? No. A4 is actually, yeah, it's not, this A4 is B0B, I'm sorry. C is something else. Just a second, this is A4. B0B is A4, okay? How is it put? Okay, this should be not C over P, but rather A4 over. Okay, let me try to draw it. So we have let me erase this so that I can draw it here. Okay, that's one possible position of the mechanism. Okay. And this is A4. This angle is phi. Okay. And this is P. And there is another possible position of this mechanism, and that is we obtain from the solution, this plus minus sign, and it is the following. It is the cross position of the mechanism, which is this. In this case, of course, our link will be, the slider would be like this. So it will be something like this, okay? And this one will be the cross. So, just a second, where is this? This is also A4. In the cross position, you see, yeah, the symmetric of this thing with respect to P, that's right. Okay, you just take the mirror image of this link, what did we call it? Link 4 with respect to the drawing P. Can you see that? Maybe it's not immediately obvious to solve for this. Okay, so we can solve for the as you see, introducing this intermediate variable P, we can solve for the necessary unknowns, which are these. Once you solve for P, you can solve for S43 and theta 14. Theta 14, as we see, there are two possible solutions. This is theta 14, and this is also theta 14. Two possible solutions can be obtained. Okay. Any questions from the audience? There is a question.
Hujam, I have a question.
Yes.
Hujam, could you go to the quick return mechanism if it's possible? This one, Hujam. Hujam, I'm having a bit of trouble finding the five revolutes. Could you just point them out just over here really quickly?
Okay, 1, 2, 3, 4, 5.
Okay, so one.
At A0, B0, A, B, and C. These are the revolute joints.
And the slider ones, they're the same ones
Sliders
on A and C.
A and C are sliders.
And what about the ground joints, Hujam?
Ground is 1. Anything is 1. Ground is here, 1.
So shouldn't they be now? Okay, ground linked.
There is only one ground, so this is 1, this is 1, this is 1. Okay.
So regardless of wherever the ground is, we just consider that being 1, right?
Yes, yes.
Okay. Okay, thank you so much.
Okay. All right, if there are no other questions, that's all for today. Thanks for listening. All right, then there will be the quiz on Friday. I will inform you about it with email. Okay, it will be online. Goodbye then.
Have a nice day, Hocam. See you later.